Multiplying a number by 3 can always be undone. Just multiply by 1/3. But multiplying by 0 is different. No operation recovers what you started with. The information is gone forever. Matrices have this exact same split. Some matrix transformations can be cleanly reversed, others flatten entire dimensions and destroy information permanently. This video covers 3 ways to identify which case a matrix falls into and a proof that the singular case is truly logically irreversible. A square matrix A is invertible if there exists another matrix called A inverse, such that A inverse times A equals the identity matrix, and A times the inverse also equals the identity. The identity matrix is the matrix analog of the number 1. It leaves every vector unchanged. In general, both equations are required. But for square matrices, a remarkable fact holds. Verifying just one equation guarantees the other automatically. This shortcut fails for rectangular matrices, so it is not trivial. Terminology to know. An invertible matrix is also called non-singular. A matrix with no inverse is called singular. These two categories form a sharp dividing line in linear algebra. Here's what invertibility looks like geometrically. Start with a grid of vectors in two-dimensional space. Each dot represents a vector evenly spaced across the plane. Now apply an invertible matrix A to every vector in this grid. The grid distorts. It stretches, rotates, and shears, but it remains a full two-dimensional grid. It never collapses down to a line or a single point. Every output came from exactly one input. Nothing's lost and nothing collides. Now, applying A inverse reverses the distortion entirely, snapping every point back to its original position. This is the geometric essence of invertibility. An invertible transformation preserves all information. Every input maps to a unique output, and every output traces back to a unique input. The grid can be warped, but it can always be unwarped. Now consider the matrix A with entries 1 and 3 in the first row and 2 and 6 in the second row. This matrix is singular. It has no inverse. We'll prove this 3 different ways. First, the determinant test. For a general 2 by 2 matrix with entries A, B, C, D, the determinant is A times D minus B times C. For our matrix, A equals 1, B equals 3, C equals 2, and the D equals 6. So the determinant of A equals 1 times 6 minus 3 times 2. That gives us 6 minus 6, which equals 0. And when the determinant is 0, the matrix is singular, meaning it has no inverse. Second proof, column geometry. The columns of A are the vectors 1, 2, and 3, 6. Notice that 3, 6 is simply 3 times 1, 2. Both columns point along the same line through the origin. The line y equals 2x. Now here's the key insight. Any product A times B produces columns that are linear combinations of A's columns. Since all of A's columns lie on a single line, every combination also stays on that same line. But the identity matrix requires the column 1, 0 as its first column, and that vector sits off the line y equals 2x entirely. So no matrix B can ever satisfy A times B equals the identity. This gives us our second proof that A is singular. The determinant and the column picture are useful, but the deepest reason this matrix has no inverse comes from the null space, the set of all vectors x, where A times x equals 0. Take x equals the vector 3, negative 1. First row, 1 times 3 plus 3 times negative 1 equals 3 minus 3, and that's 0. Second row, 2 times 3 plus 6 times negative 1 equals 6 minus 6, which is also 0. So A times the vector 3, negative 1 equals the 0 vector. And here's the critical insight. This matrix sends a non-zero vector to 0. And that information is destroyed. No inverse can look at the output 0 and then know whether the input was the 0 vector or the vector 3, negative 1, or any scalar multiple like 6, negative 2. Multiple inputs produce the same output, so the transformation cannot be undone. Now we make this airtight with a proof by contradiction. Suppose A inverse exists. We've established that A times x equals 0, where x equals the vector 3, -1, a non-zero vector. Now multiply both sides of this equation on the left by A inverse. On the left side, we get A inverse times the quantity AX. On the right side, A inverse times the 0 vector is just 0. So we have A inverse times AX equals A inverse times 0. By associativity of matrix multiplication, the left side becomes the quantity A inverse times A times X, and the right side is still 0. But A inverse times A is the identity matrix by the very definition of an inverse. So the left side simplifies to the identity matrix times x equals 0, and the identity matrix times x is just x. So we conclude that x equals 0. But wait, we chose x to be the vector 3, -1, which is clearly not 0. This is a contradiction. Therefore, our assumption must be wrong, and A inverse cannot exist. Notice that this argument doesn't depend on any particular method for finding inverses. It eliminates all possibilities at once. The converse holds too. If AX equals 0, only when x is 0, the columns are independent, and the inverse exists. A non-trivial null vector is the exact dividing line between invertible and singular matrices. We've now seen 3 different lenses on the same truth. First, the determinant test, AD minus BC equals 0. For our matrix, 1 times 6 minus 3 times 2 equals 0. Check. Second, column geometry. Both columns lie on the same line. The columns are proportional. Both sit on the line y equals 2x. Check. Third, the null space. The vector x equals 3, -1 gives ax equals 0. A non-trivial solution exists. Check. All 3 are equivalent conditions for a square matrix being singular. The unifying idea is this. A singular matrix collapses the dimension of its output space, squashing 2D onto a single line. This collapse is irreversible. This dividing line, where the ax equals 0 has non-trivial solutions, appears throughout linear algebra, governing systems of equations, eigenvalues, rank, and dimension. The invertible matrix preserves all information. The singular matrix has a permanent blind spot. If a matrix sends any non-zero vector into the void, no operation in existence can bring it back.